let's take some time to discuss polyprotic acids. We said that polyprotic acids ionize in step, and each hydrogen removal has its own separate Ka. So let's say we have a triprotic acid. There's a Ka for the first removal, and the second one, and the third one. And each time you remove a hydrogen, we said, or you remove a proton, it becomes more and more difficult. So that means that the Ka is going to become smaller and smaller as we remove each proton. Generally, the difference in Ka values is great enough so that the second ionization does not happen to a large enough extent to affect the pH. Most pH problems just do the first ionization. One of the exceptions is sulfuric acid. And we use the sulfuric acid concentration as a hydronium ion for the second ionization. And the A2 minus is going to be equal to the Ka for the second, as long as the second ionization is negligible. In this table, we're just listing some of the polyprotic acids. Like sulfuric acid, we said is a diprotic, and the first removal of a proton is a strong dissociation. But notice that the removal of the second one has a Ka value of 1.2 times 10 to the minus second. Oxalic acid is a diprotic acid. Sulfurous acid is a diprotic acid. Phosphoric acid, it has 3 protons. Citric acid has 3. Ascorbic acid has 2, and carbonic acid has 2 protons that can be removed. So these are all examples of polyprotic acids. So let's do an example where we're looking at finding the pH of sulfuric acid, and we have to worry about the 2 protons coming off, since it is a diprotic acid. So I'm writing here the equilibrium reaction for the sulfuric acid in the first removal of the proton. And then the second reaction is the removal of the second proton to form the sulfate ion. The Ka for the HSO4 minus is 0.012. So I'm going to set up my ice table. I have the initial concentration of my HSO4. Because remember, the first reaction, I'm going to assume, since it's a strong acid, to go to completion. So the concentration of the HSO4 minus is going to be the same as my initial concentration of my H2SO4. So that's where I'm getting the 0.01 from, because I assume that this first reaction, since it's a strong acid, it's going to be a one-way, so it completely dissociates that first proton. So when that dissociates and all that gets converted into the HSO4, I also create equivalent of H3O plus. So that concentration here is 0.001, and the concentration of the hydronium in this is 0.01. Well, now that HSO4 can then establish its own equilibrium, because this is a weak acid, so I have that 0.01 for the initial concentration of my HSO4. Well, I can lose part of this and form part of my SO4 minus and some of my H3O plus. But I initially have some protons in there from the first reaction, so I have to take that into account. So this is a little bit new compared to some of the other reactions that we did. Okay, so I set up my change here, my ice tables, and my equilibrium values. Now I've written my mass action equation for my second reaction for the HSO4 going to form the sulfate ion and the hydronium ions. So it's products over reactants. So in here, this first step, what I've done is I plugged in my Ka for my HSO4. So I've just plugged this in here. And I multiply both sides by my denominator to get rid of the denominator. And then I move everything to one side so I can do the quadratic equation. So I get it 0 equals x squared plus 0.022x minus 0.00012. And if I use the quadratic equation, I should get either x equals minus 0.027 or 0.0045. Now I know that it can't be a negative because the reaction has to go in the forward direction because I don't have any sulfate. Now, if I want to find my H3O plus concentration, we found what our X was. So I'm going to do the 0.01 plus X, and I get an H3O plus concentration of 0.0145. So I'm getting close. They want to know the pH, and I found the hydronium ion concentration. So if I take the negative log of the hydronium concentration, I get a pH value of 1.839. Let's also discuss the strengths of binary acids. So the more polarized the bond, the more acidic the bond. So if we're looking at some molecule HX and we have a partial positive charge on the H plus and a partial negative charge on the X minus, so we have a big difference in electronegativity. The bigger the difference in electronegativity, the more polarized the bond, the more acidic the bond is going to be. So the binary acid strength increases to the right across a period. So as you go across, things get more acidic. So comparing hydrogen oxygen compound would be water, and then HF, so water is less acidic than HF. But the stronger the HX bond, the weaker the acid. So you have to consider the covalency of that bond. And as you go down, you get decreasing bond strength. And as you go down, since you get decreasing bond strength, you get increasing acidity. So as you go down the periodic chart here, HF is a weak acid, but the acids get stronger. So HCl, HBr, and HI. Those are all strong acids. These all completely dissociate. But HF is a weak acid, and it does not completely dissociate. Now you have to be careful too. Don't just assume because it's a weak acid it's not dangerous. HF is extremely dangerous. HF will dissolve glass. HF has to be contained in a special plastic container, because if you put it in a glass container, it'll eat through it and just spill out. And also, if you get it on your skin, it will leach down to your bone and cause problems. And there are actually many documented stories of graduate students or other people that were not aware of the dangers of HF accidentally dying from getting HF on their skin. So you have to be very careful. Just because it's a weak acid does not mean it's not a dangerous acid. Again, I want to revisit the strengths of oxyacids. Remember, oxyacids were acids that contain oxygen and hydrogen in the formula, like sulfuric acid or nitric acid. Those are oxyacids. And we said the more electronegative the central atom, the stronger the acid. And that's because that difference in electron negativity helps weaken the OH bond. Because if the central atom is, let's say we've got Y here, and that's that central atom is very electronegative. If it's also pulling electron density from the oxygen is also very electronegative, there's not much electron density to share with the hydrogen. Hydrogen gets a little miffed and says, fine, I'm leaving, you can have my electron, and it leaves as the H plus, so it makes it more acidic. And then the more oxygens attached to the central atom, the stronger the acid. Because the oxygens are very electronegative, it's going to be pulling electron density from that central atom, so it even polarizes the bond even further. So it further weakens and polarizes the OH bond. So more oxygens generally mean a higher oxidation state for the central atom. So we've discussed the Arrhenius definition of acids, and that's our first very basic definition, where we said that an acid is in an aqueous solution and it produces protons, and a base is in an aqueous solution and it produces hydroxides. Then we said that definition wasn't good enough. And then we went on to the Bronsted-Lowry definition, where we said the acid is the proton donor and the base is a proton acceptor. Where there's another definition and way to classify acids and bases, and that's Lewis acid-base theory. And this Lewis acid-base theory is going to be very important for our understanding of organic chemistry, and in particular coordination compounds and transition metal chemistry. So Lewis acid-base theory is a way of electron sharing. And a Lewis base is an electron donor. It is a nucleophile. It loves the nucleus. So it must have a lone pair of electrons. And a Lewis acid is an electron acceptor. It is an electrophile. It is an electron lover. It wants electrons because it's electron deficient. So when a Lewis base gives electrons from its lone pair to a Lewis acid, it forms a covalent bond between the molecules. So we have a nucleophile with a lone pair. So this is our Lewis base. It will give that lone pair of electrons to the electrophile, which is our Lewis acid, and it forms an adduct here. So the product between these two, that relationship when it shares that electron density, this is an adduct. And Lewis acid base theory is a very general, useful definition of acid base theory, and all other acid base reactions can be classified and studied using Lewis acid base theory. So here we've got an example. We want to complete the following Lewis acid base reactions, and we want to label the nucleophile and the electrophile. Notice here with the carbon here, we've got 1, 2, 3, 4, 5, 6 electrons around it. We should remember from Chem 1A that this is not meeting the octet rule. This is electron deficient. This is why we have this positive charge here on the carbon. And here we also have a hydroxide. So the hydroxide is a nucleophile. It has a lone pair on it. So it actually has 3 lone pairs, but we're going to show one of these electron pairs, and it goes and attacks that carbon center, which is electron deficient. So if the hydroxide ion has lone pairs, it has electrons, it loves nucleuses, so this is the nucleophile, and then attacks the carbon, and the carbon is considered an electrophile because it's electron deficient. It loves electrons, so it's going to take the electrons from the nucleophile and it's going to form a bond. So we see this bond being formed here between the carbon and the oxygen. So let's try that again with the BF3 and HF. So we draw the Lewis dot structure of HF. We've got the lone pairs on the fluoride. And if we draw the BF Lewis dot structure, remember that that is electron deficient. So it's going to accept electrons from the HF. And when it does, it actually cleaves the bond and actually makes this proton acidic. So the BF3 is our electrophile because it is electron deficient. It wants more electrons. And the HF is our nucleophile. It has lone pairs. It can share those lone pairs with something else. So it wants to be with the other positive charged things or things that are another nucleus. So when the electrophile and nucleophile get together, they form that bond between there, so you get the BF bond being formed. In the reaction of calcium oxide and the SO3 sulfur trioxide, if we draw the Lewis dot structure of the SO3, this has a trigonal planar geometry, and this is sp2 hybridized. And the calcium oxide, think of that as ionic, so calcium 2+, and the oxide has a 2- charge, so it has a full octet around the oxygens. So the O2- has all these electrons, it's negatively charged, so this is going to be our nucleophile. It loves nucleuses, so it's going to attack the sulfur. The sulfur can accept that electron density, so it is going to be the electrophile because it will be electron loving. It will accept the electron density from it, and it forms the sulfur oxygen bond there, that adduct. Here we get a chance to talk about some of the applications of acid and base chemistry. So first of all, what is acid rain? Natural rainwater has a pH of 5.6. It's naturally acidic mainly due to the carbon dioxide, because carbon dioxide when dissolved in water forms carbonic acid. But rainwater with a pH lower than 5.6 is called acid rain. And acid rain is linked to damage in ecosystems and structures. Many natural and pollutant gases dissolved in the air are non-metal oxides. For example, there's SO2, there's carbon dioxide, there's NO2, and these non-metal oxides are acidic. For example, carbon dioxide dissolving in water to make carbonic acid. Sulfur dioxide will make sulfuric acid. And there are also processes that produce non-metal oxide gases as waste, and this increases the acidity of rain. And not just man-made processes such as combustion of fuel, there are also natural sources of these gases. For example, volcanoes are notorious for producing sulfur dioxide, and that sulfur dioxide produces the sulfuric acid. And there are also some bacteria that produce some of these non-metal oxides. Now, weather patterns may cause rain to be acidic in regions other than where the non-metal oxide is produced. So just because you have your non-metal oxides being produced in that area, the wind or other weather patterns may carry them to other areas and produce the acid rain. This graph is just illustrating sources of SO2 from utility plants and based on different years. You can see in the East Coast there are higher levels of sulfur dioxide emissions. And these figures here just kind of show you some of the damage associated with acid rain. So you see the erosion, and the features on this statue are not as nice and well defined as they originally were, but also you can see some of the death of some of the vegetation in areas where there's a high concentration of acid rain. So acids react with the metals and materials that contain carbonates. That acid rain damages bridges and cars and other metallic structures. And the acid rain also damages buildings and other structures made of limestone or cement. So if you'll remember in our previous recorded lectures, we talked about acids reacting with calcium carbonate and other things like that to produce carbon dioxide. Well, this is limestone, is calcium carbonate. And so you can see that that also reacts with the acid in the rain, and it washes away the outer exterior of the building or the cement. But acid rain also, one of the effects is it also disturbs the aquatic life because it actually acidifies the lakes and other bodies of water. And another problem with acid rain is that because the acid will dissolve some metals, it'll actually cause some of the minerals from the soil to be leached, and they have a higher free metal concentration in the soils, which can also cause havoc with some of the life forms. So this ends our recorded video lectures. We'll discuss and do more problems in class.